All right, in this video, I'm going to show you how to set up and run an example simulation using the MUPFES solver, which is a multiphysics solver written by Dr. Madi Mesmali. And so the example simulation we're going to set up is going to look like this. And so here's our geometry. And what we're going to do is we're going to name the faces, the outlet faces, there are four of them. We're going to name them top. We're going to name this face bottom, this face right, and this is left. And the reason that left and right switch is because usually when we look at medical imaging data, we're looking as if we're looking at the patient from the front, and so their left is our right. And so that's how we're going to name these outlet faces. And then the the wall, this just everywhere else in the vessel, we're going to name wall. So that's how we're going to assign the naming in our simulation. And at the top and the bottom outlets or inlets, we're going to just directly assign a pressure, and the pressure is going to be just a sine wave that's centered around 30 millimeter mercury. And at the outlets, left and right outlets, we're going to assign a RCR circuit with these values of the proximal resistance and distal resistance and the capacitances. And so these are the values that we're going to assign. And so this is just to show you what we're trying to do. This is the simulation that we're going to try to set up. So to run a MUPFES simulation, you will need these files. So what these files are is, first of all, you need files that describe the geometry of the 3D region that you're trying to simulate. And so that would be these files. And they might look a little bit different depending on your geometry, but basically you need the connectivity file and the coordinates file for each geometry. And then these EBC and NBC would describe all the different faces on your geometry. So for each geometry, you will need these two files and then a bunch of these face files. And I'll show you how to generate these in a little bit. We also need this configuration file, the .mfs file. The configuration file will contain information to tell the solver how it's supposed to solve the equations. And then lastly, we need information about the boundary condition. And so we would need two files in this folder. And the two files are going to be, I'll show you how to generate them, but one of them is the initial value file, and the other one is we're going to compile this program. It will generate an exe file that we will need. And so these are actually all of the files that you need to run a MUPFES simulation. So the geometry files, the configuration files, just one file, and then two files to describe your boundary conditions. So now I'm going to show you how to generate these files to run the simulation. So the first item I'm going to tackle is I'm going to show you how to generate these files that describe the geometry. All right, so what you have, you would start with a 3D model. So we've got our 3D model here, the TCPC file, and I'm just going to make a new folder, and I'm going to call it mesh, and I'm going to have to mesh this 3D geometry to get those geometrical files that we need. So I'm going to put this in this model in this folder here, and I'm going to cd into this folder, and I'm going to open Simvascular. Okay, so what I'm going to do is I'm just going to mesh this geometry, and so I'm going to go to the meshing tab, and I'm going to open my geometry file, load it, and then this model is in centimeters, and so I'm gonna pick my maximum edge size to be 0.1 centimeter, which is 1 millimeter, and I'm gonna run the measure. And so this might take some time depending on how fast your computer is. And so basically now I'm meshing the geometry, and then I'm gonna have to save the result of the mesh once it's done. Okay, so it's done, and we've got 360,000 elements, which is not too bad. Okay, so it's done meshing, and I'm just gonna save it. First of all, in order to have the program not crash, I have to uncheck this inflow phase. Okay, so now it's unchecked, and I'm gonna write output files, and that's gonna write my mesh into my hard drive. Okay, so now we're done meshing, and these are the files that it generated. So in your mesh surfaces, it's going to contain all the files that describing your faces, the faces of your mesh. So not the volume, but just the faces. Now, if we look at the files that we actually need, a lot of these EBC and MBC files that are in here. And so the way that you would tell what they were, if you get a bunch of these, then you wouldn't know which file is describing what part of the geometry. I'm going to show you um, how to tell which file is describing what. So I'm going to go into this folder and open ParaView, and I'm going to load all of these VTK files. And I'm going to load them separately, so um, I won't explain exactly why, but you need to load them this way instead of loading this wall but as a one entity. You just need to load them like the way I did. And so now you've got this geometry. And the way that you would tell which is what is you would toggle these items. So the IVC here, okay, so I toggle it and I see that IVC is this face right here. The LPA is right there, this one right here. And a lot of these walls are describing different parts of the wall. And I've named these purposefully in the solid model, so they all say wall something, so I know that they're part of the wall. And then we could. So this is how you tell which face is what. And so once you know, then you will be able to, in your configuration file, be able to point to each one of these files to the correct face. I'm going to show you one little trick that I use. You could use with Symbascular to kind of make this a little bit simpler. So right now there's a lot of these wall faces that are all different files, and that's kind of annoying because I mean they're just the wall, and I don't want all these files describing the wall. So I want to combine all of these wall files, and because I've named them wall underscore something, there's actually a function in Symbascular that will make that easy for you. And let me go back to Symbascular. I'm going to go to Simulation tab. And so there are these two commands. After you run the mesh, you could just run these two commands to combine all of the wall files. So here's wall underscore dot star. So anything that's named wall underscore something will be combined into one file that's called wall.ebc. Okay, so I'm just going to execute these. And this is right after I did the mesh, so everything's still loaded in here. Okay, so now I've done that, and I've combined everything into the wall file. So now it's generated these two files that describe all of the walls. So now in here, I have all these wall something that's been combined into those two files outside of this folder. So I've got these faces that describe the outlets, and then I have the wall files here that describe the wall. And then so that takes care of all of these files. And then these two, the connectivity and the coordinate file, they're basically right here. You'll get two of these files. So now we have everything that we need for the geometry. And so what I'm gonna do is I'm just gonna create another folder, and I'm gonna call it test simulation. And so that as I generate these files, I'll put them in here. Okay, so we've got these two, and then the wall that we need. I'm gonna drag them out here. Mesh surfaces. Then we have the I'm gonna rearrange them. So we have the outlet faces. I'm gonna drag them here. So that's all you need. So these files describe all of the surfaces in my geometry, and plus we have the connectivity and coordinate files. Now you notice these look a little bit different because they're zipped. And actually, it's important to unzip them because otherwise your solver would not be able to read them. So I'm going to go into the folder, and I'm just gonna unzip everything. G unzip star. Okay, so now everything's unzipped, right? So now it's good. Okay, so let's go back to our to see what else we need. So here's the ones that I created. So we've got all the geometry files, and we also need this example, uh, this .mfs file, which is a configuration file that tells the solver what we're doing. And so actually, I'm gonna just use this right here. So we've got the geometry files, and now I'll explain to you what's inside this configuration file. So if you open this, you could use this as a template if you want to. The structure is basically the same, so you change a couple of things for what you need for the simulation. Okay, so it's actually, this file is pretty simple. A lot of the lines are self-explanatory. So here, the number of spatial dimensions, we're doing a 3D simulation, so it's 3. Depending on how many time steps you want to simulate, I've got 10,000 right here, so you could pick that. This is the size of your time step. So right now it's set to 1 millisecond time step, and you could adjust this as you need. The initialization time step is, there are some simulations that might be unstable, it might explode. So if I just run 1 or 2 steps to initialize, what this will do is it will run the first 2 steps with a time step size that's a tenth of what you set right here. And so with the very small time step size for the first 2 steps, it will help stabilize the values, the pressure and velocity values in your domain, so that it's less likely to explode. So you could use this to help stabilize your simulation. If this is set to 1 versus 0, then if you have a simulation that was running and then something happened, you stopped it, and this is set to 1, when you launch the simulation again, it will continue from whatever you were left with. And if it's 0, then it will restart the simulation from time 0, and actually it will erase everything that's in that folder. So you want to be careful if this is set to 0, that you don't erase the simulation that you ran before. And this is how often you want to save the files that are contain the current simulation data. So just in case if your simulation gets stopped, then when you restart it, it'll only go back 50 time steps or less to the previous save, and it'll start from there. So you could decide how often you want to save. You don't have to worry about this. This is the name of the files, of the output files. This is, you can set how often you want to save the result files. And so the 3D velocity and pressure and so on information, the program will save as the VTK file, which you can then view later. And this tells the program how often you want to save these files. So right now it's setting to be saved every 100 steps. You don't have to save the entire simulation. If I run 10,000 steps here, I don't want to start saving from step 0. I just want to save the last cycle. And so you can set at what time step you want to start saving these results. And this, if you set to 1, then at the end, it'll average all of the VTK files and then give you one averaged VTK that describes the average of all your time steps from the VTK files that you've saved. And then you don't have to worry about these. Okay, so the first part kind of describes several aspects of the simulation. In this section right here, you're adding the mesh. So this describes the geometry of what you're trying to simulate. And so first of all, you have to tell it what the 2 coordinate and connectivity files are. So you just put the name of the coordinate file and the connectivity in here. And if you put it in the same folder, then it's just the same. You don't need anything here in front of the path. So it's put the name here, and you have to add all of the faces. So that includes the wall face and also the face of all of your outlets. And so here, for each face, you need one of these blocks. This right here is the name that you want to give this face. So you could give it whatever name you want, but then in the rest of your program, you will refer to this face using the name that you give it. Okay, so for the wall, I'm just gonna name it wall. And here, you would put the name of that file, the EBC file that contains the wall information in here. And so you do the same for the outlet faces. The bottom one, I'm just gonna name bottom, and that's the IVC, and so on. And so the order by which you add these faces will be the order that the results are output. And I'll show you what the result file looks like later. But the order here determines how the results are printed. Okay, so now you've added your mesh. The next thing you need to do is to add uh, the fluid equation, so the Navier-Stokes equation that you want to solve. And so you need this block here that adds the fluid equation. You don't really have to change too much here. You have to make sure the density and the viscosity, these are the two things you want to set. And so you want to set the density of the fluid and the viscosity of the fluid. And you just have to be consistent with what unit system you want to use. So you could use CGS units, which is what this simulation is in. So the model is in centimeters. And so I want to use G gram for mass, a second for time. So you just set your density and viscosity correctly according to the unit system that you want to use. And then this part right here, you want to set the boundary conditions of all of your faces. Again, that's including your wall and all of your outlets. And so in this case, we're going to use the CPL-BC to set our outlet boundary conditions. And so we need this block here. And I'm going to tell it where these boundary condition files are. And in this case, I'm putting it in a folder. And so I have a path to this folder right here. And then the two files that I need is the initial value file and then this cplbc.exe file, which we'll generate in a minute. So I'm just telling it the path to these two files. And then the solver needs to know which face is coupled to which boundary condition, right? And so we need to add boundary condition for all of the faces. For the wall, and again, the name here, you're using whatever name that you set here is the name that you're going to use from now on to refer to that face. And so I'm going to add a Dirichlet condition to the wall, which is very typical. You know, you have a rigid geometry, then you're setting no slip condition on the wall. And so I'm going to set a Dirichlet condition with a velocity of 0, and the profile can be anything because there's no velocity. So this is my no slip wall boundary condition. And then at the different outlets, I have to set different conditions. And so to review, we've got pressure here and then RCR here. And because the first element of the RCR is the capacitor, or the first element that requires a differential equation is a capacitor, then this is actually also a pressure condition. And so we have Newman condition on all of them. So we're going to set that right here. So we have a Newman condition that's coupled to our CPL-BC. And then so you could kind of just set the same thing for all of these. So it's just to add the boundary condition. Okay, so that's pretty much it. That sets all of our fluid equations that you need. And this is all you need to actually run the simulation. I'm going to do a little something extra here. You don't have to do this, but I'm just going to do this for this simulation for fun to show you what it looks like. The additional thing I'm going to do is I'm going to release some tracers at the top and the bottom faces just to see where they would go. So normally you would have flow coming in here and then coming out from these two branches, and flow coming in here. And so I'm going to release some tracers here to do a advection diffusion analysis to see how much of the flow here is going to left, to the right, and so on. And so I'm going to add a heat equation here to release those tracers. And so this block defines the heat equation, and then these two blocks tell me which of the faces I want to release this tracer. And so I want to release at the top, at the bottom face. So I have two blocks here. I use Dirichlet condition and set the value to 1. And so that just means the tracer concentration at those two faces is 1, and they'll get released, and we can see where that goes. So this is just a little extra thing that I want to do in this simulation, but you don't need it for the fluid simulation. This is extra steps. Okay, so this is how you would set this configuration file. It's pretty simple. So now you've got everything here. The last two things you need is the boundary condition files, and I'll show you how you get those. Okay, so the three files that you need to edit are these three: the faces, initial values, and user.f. So I'm going to open these. Okay, so let's take a look at this user.f first. Here's you want to assign the boundary conditions using this file, and I have another video that shows you how to convert a circuit into this type of differential equation and how to code it. So you could you could check out that video if you don't know how to do this. But here I'm just going to talk about the parts that's relevant to the multi-scale simulation. So here, what we've got is that you could have a unit conversion between what's in this file and what's in your 3D simulation. So it's possible for your 3D simulation to run in CGS units, but here it's more convenient for me to use millimeter mercury as pressure units and to use milliliter as flow units, so milliliter per second as flow units. And so just depends on what unit I want to use as pressure and flow in this particular file. I can have a conversion factor that will make everything consistent. And so in this case, I'm using millimeter mercury in here as pressure, where use CGS in the 3D domain, so I need a conversion of 1,333. And then for the flow, CGS, I'm using millimeter per second here, and I'm using centimeter as the length unit in the 3D domain, so they're the same, so the conversion is just 1. And then you don't have to change anything else here. The rest of this is basically how you would set up a circuit with this type of code, and you could check the other video on how to do that. Okay, so I'm gonna go into this faces file first to show you what needs to be in here. And so the faces file tell the simulation which face is corresponding to which variable in your user.f. And so here's the face number. These in each block, there's 3 lines, and the important things in each of the block is this number right here. So this is face number 1, and you're assigning face 1 to the top face. So this is whatever you defined in your configuration file, and you're saying that the value of whatever quantity that you're assigning to that face. So in this case, it would be, I guess, pressure, because it's a Newman condition. The value of that quantity is described by x4. So this number 4 is the x's, the x numbers that you're using in here. And so actually, I'll tell you that in this particular setup, I'm setting x1 to be this pressure, x2 to be this pressure, x3 to be, let's see, x3 I'm using as a time variable to keep track of time, and then x4 I'm using it to be the pressure at these 2 points. So I'm actually assigning the same pressure waveform both at the bottom and top. So that's my x3. Sorry, that's x4. x3 is time. x4 is those pressures. And then I have x5 and 6 here. That's just to print out additional parameters. Again, you could check the other video on how to work with those x's. So this face, you need to have one of these block for each of your outlets You don't need one for the wall, but you need one of these blocks for each of your outlet faces that's coupled to a boundary condition that's described by the CPLBC. Okay, so the bottom one is also pressure, so that's x4. The left one is I said is x1, so it's associated with this pressure here, and there's the resistor in between. And I'll tell you how to deal with that. So x1, x2, and so on. So that's how you would set the face .f file. And then the index here we will use when we use the flow that's being returned from the 3D simulation to your 0D code. This number tells you which flow corresponds to which phase, and I'll show you what that means in a minute. Okay, so here we got our time, which we set to be x3, and then we have a little code here that calculates the flow waveform, the pressure, the input flow waveform. And I have another video that actually shows you how to prescribe a time varying waveform that you can check out if you don't know how to do this, but that's what it is. So here's our pressure. In the differential equations, here we have F1 and F2. That's describing these two capacitors here. And so let's just look at F1 here. So if we want a differential equation that describes this pressure, we want to take this flow that's coming into the capacitor and then subtract this flow that's coming out of the capacitor and then divide it by the capacitance. So this flow, maybe I'll just move this over here so you can see. So let's see. This flow into here is actually given by the 3D domain, right? This is a Newman condition where the 0D is prescribing pressure to the 3D, and the 3D is providing flow information to the 0D domain. So I actually have a flow that comes out here that's given by the 3D domain, and I can use it. And so that's what I'm going to do. This flow would be Q3, and the reason that it's 3 is because of how we set this face. We're setting phase 3 to be the left face, which is this one. And so the index of the Q for this particular phase is 3. Okay? So now we've got this Q3 describing this flow coming this way to the right. And then we're subtracting this flow, which is this pressure minus this pressure, which is 0. This is ground, divided by this R. So it's X1 divided by RD1. Okay, and divided by this capacitance here. And so now you see how, depending on how you define these phases, that you would use the different Qs appropriately to assign your equations. And so the same thing with this one right here. So we've defined this to be Q4, right? This right here coming out to the right, this flow is Q4. We've defined that as Q4 right here. So phase 4 is the right phase. Okay, so if we want this flow, we would write Q4, and then here's the rest of the differential equation. Okay, so the next thing you need to do is you're trying to. This code is a boundary condition that tells your 3D domain what pressure is at each of these phases. Now, what we've calculated here, x1 at this point, is the pressure at this point, not the pressure at this phase, right? And so if in order to provide the pressure at this phase, we need to account for this resistance here. And that's what these offset lines are. So for phase 3 and phase 4, which are these two phases as you defined in your phases.f, for phase 3 and phase 4, we're going to set an offset which is produced by this resistor. So we're going to take this flow and multiply by this resistance, which means that's the value we're going to offset the x values with, right? So in phases.f, we've said that the phase 3, the value of the phase 3 pressure is going to be x1, but our x1 is this pressure, but we actually want this pressure. So we're going to offset this pressure by this amount, whatever is caused by this resistance. And so that amount is going to be the flow through the resistance multiplied by the resistance. So that's Q3 times RP1 here. And so you do the same for the other side. And these are just additional things you can print out. So that explains these two files. And obviously you need to have some initial values that you need to prescribe to each of those x's. So you just need to put in the correct value for those. So that's all you need. We're ready to generate the file we need for the boundary condition. So once I have everything ready, I'm gonna go to this folder. Okay, so I'm in this folder. I'm just gonna type make. So now it's compiled this code here, and it's produced this cplbc.exe, which contains all the information that we've entered here into an executable that your solver, the MUPFES solver, can use to understand what's going on in the boundary conditions. Okay, so we're actually done. We have everything we need to run the simulation. So I'm gonna go back to this folder where the configuration file is, and so that's right here. And I'm just gonna launch the simulation. So I'm gonna use multiple processors. So let's say I'll use 6 processors, and I'll type MUPFES and then type the name of the configuration file, and that's it. And it's launching the simulation now. Okay, so I use 6 processors, and it's going to store the simulation results in this. It'll create a folder that's called 6procs, and the simulation results will be stored in here. So let's just take a quick look at what's going on. So you'll see these kind of text files. These describe the various fluxes or pressures that are at all of your faces. And this is where I said the order by which you prescribe the faces in the configuration file matters. So let's just take a look at this velocity output here. So you see the order of the columns, wall, bottom, top, left, right. This is the order by which I prescribe those faces in the configuration file. And so these are actually just the values of the flow rates at each time step for each of these phases. And so you have the flow rate, you have the pressure, you have the energy flux, and these two are the kind of the concentration tracer information the additional thing that I prescribed. And this all data file contains the result from the CPLBC. And so these are actually all of the X values that you assigned in user.f. And so these X1, X2, X3, X4, and so on. And these are all the time steps. And so that's it. That's how you set up and run a MUPFES simulation, and with this example. I have another video that shows you how to analyze the results using ParaView. So if you don't know how to do that, you could go check that video.